Hi everyone. So we're going to move into your unit 3. So unit 3 totally about the magnetism. So far what we talk is about electricity part. So we know that if there is a charge particle, that charge particle can have electric field, so that can have electric force, and there should be electric potential. So after we learn about this everything, we went to the circuit analysis, and we know that we can connect resistors in series, in parallel, and combination of both of those, and then we discuss about how to solve those kind of circuits to find the unknown current or to find the voltage or the resistance. So in addition to that, we discuss about how to manufacture the resistor or the capacitor and what those devices, important concepts of those devices. So now we're going to move into the magnetism. Why we need to learn about the magnetism? Magnetism is another component of your technology, because in technology, if you think your computer, so computer does not only include the electricity part. There is some magnets, there are some the motors, those everything is made up of concept of electricity plus magnetism. So now because of that, magnetism is your basically second part of your class that we're going to discuss about magnets, magnetic fields, magnetic force, and also combination of electricity and magnetism together, that will be Maxwell equations. So now this is the start of magnetism. So now in your textbook, we're going to start with chapter 22, as you know. So chapter 22 is a long chapter. Because of that, I divide this chapter into two parts. That means basically you are getting two worksheets, two homework for this part. And then next section, I'm going to actually talk chapter 23 and 24 together to one worksheet and one homework. Okay, so now under chapter 22, as you guys can see it in here, my plan for this section is basically mainly focus into magnets and magnetic force and magnetic field. So now, because of those things, there is magnetic force, then how magnetic force and electric force combine to create a cross field when they are perpendicular to each other. We call it as cross field. And when you have a current carrying coil, that coil, why do the rotation? We call it as the torque. So those will be the parts that we're going to discuss. Okay. So now let's start with the history first. So now the first thing that developed is 1263. After developed the lodestone, the 1263, they developed the compass that you guys have seen. The compass is a kind of needle that you have north and south magnet. Whenever you bring into the magnetic field, that will direct you the direction of the that magnetic field. That is called it as the compass, right? So after that, in 1600, William Gilbert found that Earth itself has a huge magnet in the center of the Earth, right? That will create a magnetic field lines around the all universe, right? And then 1820, Hans Christian discovered that electric current can create a magnetic field. That's concept we're going to learn. Electric current can create magnetic field. That means if you bring the compass around the current carrying wire, you're going to see the deflection of the needle on the compass. And then 1830, we're going to learn that also Michael Faraday and the Joseph Henry independently discovered that magnetic field can produce the current. That means magnetic field, actually you can use it as a source to create the magnetic or electric current. Okay, and then 19th century, James Clerk Maxwell developed the mathematically developed the electricity and magnetism together, we call it as unified theory of electricity and magnetism. That's the Maxwell theory. We are not going to discuss the mathematical derivations and mathematical writing of the Maxwell equations, because those are actually complex equations that we discuss in advanced level classes. But we're going to basically get an idea of what these Poe equations means to us. Okay, and then 19th century, again, end of the 19th century or beginning of the 19th century, the superconductivity developed. That means they found that there is a certain temperature, we call it as Curie temperature, that will lose the magnetism of magnets. So those we call it as the Curie temperature. So after 19th century, we are still working with or discovering superconducting materials, but that's the first discovery of the superconducting material. That means you can basically have a superconductor that will create the magnetic field lines that you can levitate the thing, so you can bring the train travel with the this superconducting behavior. That means basically superconductivity does not have a resistance until some temperature range. That very low temperature resistance is 0. Okay. And so magnetic field. So you remember that when you move into the electricity part, we start with the electric force, but in magnetism, we're going to start with magnetic fields, because there is a reason that for that. Magnetic force actually a very hard definition or very hard way to explain the magnetic force into the magnetic field. Because of that, we start with magnetic field first, and then we go back to the magnetic force. There is no specific like definition. This is the magnetic force that we can say, because there are many ways that we can define the magnetic force. That's the reason. Okay. So now a simple example is, you remember these positive and negative charges. Electricity part, we know that electric field lines will create in this way. There is no question on that. We learned that, right? But when you come to the magnetism, magnetism does not have the positive and negative charges. What it does is it has the north and south poles, similar to positive and negative. But in this case, we have poles, right? So these poles, north and south poles, will create a magnetic field. Those are, we call it as magnetic field lines. That, as you can see it in here, you see that magnetic field lines going start in north and end in south, but that is not true. So magnetic field lines always make a circular pattern. That means there is no starting and ending point as electricity does. Electricity has a starting and ending point of the positive and negative charges. But here all are circular patterns. In addition to that, this north and south, magnets always stay with north and south. That means magnets cannot stay as a monopole. You remember that in electricity, we can keep the positive charge separate from negative charge, and positive charge will create electric field line outwards, negative charge will create electric field line inwards. So now they can separate, there is no question. But that means they can stay as monopole. Monopole means single pole, right? Single charges. But in magnetism, the magnets that we have does not stay separate. They have to stick into together. That means they are staying like a magnetic dipole as always. So now north and south will act like positive and negative, but they are actually poles. In addition to that, since north and south magnets staying together, the poles staying together, you never can separate the magnet. You cannot divide into pieces and separate north is this part, south is this part. When you break into small pieces, each piece you break should have a north and south always. They cannot separate. That's why it's called no magnetic monopoles. They are staying as dipole always. Okay. So now So now the magnets, you definitely know that the similar to electricity, north and north will be repel each other. As a simple example, I have two magnets, right? So now you see that these two magnets, when I try to bring it closer to each other, they're going to attract each other. So that means one is north, one side is north, other side is south. That's why they will keep attract. But if I try to bring a same pole, that means I'm going to bring a south pole in here, south pole in here. So I cannot bring them together. They will automatically go backward because they going to repel each other. Repulsion, attraction will stay the same, but you cannot say there is a force in between these two. Only thing you can say is there is magnetic field in between these two. Because of that, they're going to attract. There is magnetic field in between these that will similar to the repel each other. Because of that, they will not attract each other, right? So that's how the magnets attraction and repulsion will work. So now, as we mentioned, there is a magnet, huge magnet inside our Earth, but this magnet is not actually represent your geographic faults. Geographic faults, you have north and south faults, right? So geographic north will be in this way. It's mentioned in here. Geographic North Pole, geographic South Pole. This is where that we call north and south, right? But the magnet inside the Earth is not representing that at all. So, but this magnet will be rotating around the time interval that can keep rotating, and around it's detected that around 300,000 years it will totally flip the north and south. Okay, so that will take longer time, but it is not staying rest at the Earth center. It keep changing with the time. Okay. So now we're going to move into the magnetic force. This is the reason that I told you that magnetic force, I cannot say it is something that I can calculate directly without knowing the other things, because magnetic force will not create like without charge particle. So you should have a charge particle. That is one way to define it. You should have a charge particle that is moving with some velocity, right? So this is the charge particle. If it is moving with velocity, this is charge, as we already know. And this is velocity of the charge particle. And this is definitely, we know, magnetic field. Right, then there is a magnetic force. So now magnetic force, so it is very important that you understand this concept very clearly, because we're going to discuss a lot of things on this chapter and next chapter. So they are all combined, but they are different concepts, right? So now the concept I'm going to teach you here is, if there is charge particle moving with velocity v inside the magnetic field, then that charge particle feel the magnetic force that will be able to calculate by using this formula. So that is what the magnetic force on that moving charge particle within the magnetic field. Those three things are important. It should have a charge particle, should move, right, with some velocity, and there should be a magnetic field. Then that particle feel the magnetic force that will be able to calculate by using Q, V, and B. So now I put it in the cross product. I know that we are not talking about cross and products in your class. That will be for the Cal-based class, but this cross product gives us some information. When you multiply two vectors by using this cross sign, that will give you a vector, right? Because I just want you to show you that velocity and v are both are vectors. Then if you multiply these two vectors together, you're going to get the another vector, that is the cross product is, right? But sometime we still multiplying two vectors, but not using cross product. That is, we call it as dot product. Similar to the work done you learn in your physics 1 class. Work done is force times distance, right? Work done equal force and distance, and we take the dot product there because your work done is a scalar quantity, right? If it is a dot product, it will be a scalar. If it is a cross product, that will be a vector, because I just need to point out that in here. But other than that, this dot and cross has another meaning. It will take the sine of theta and cosine of theta. You remember that in work done, definitely we discuss about the work done. That my pen is stopped working. Okay, so now when you have the dot product, you remember that the work done case that we discussed about the work done equal cos times distance, but we wrote it as cos distance and cosine of theta. Theta was the angle between F and D. That means when they are parallel or anti-parallel, you're going to get the maximum work done, right? But if it is a cross product, you're going to get the sine of theta. Because of that, if it is a sine of theta, you know what will happen in here. Then QVB, you're going to write it as this formula, sine of pi or beta, whatever angle in between V and B is the pi in this case. So now we know that sine 0 give you the 0. That means this, if these two vectors are perpendicular to each other, then you have a third vector that will be not 0. That is depend on your Q, V, and B, right? When phi goes to 90 degrees, your pose will be equal to Q, V, and B. Right? That's the maximum magnetic force that you can get. So that's the idea about the cross and dot product in simple version, right? But there are a lot of mathematical explanation for that. But only thing that we need to understand in here, the magnetic force will be able to calculate by using the formula that I have it in here. This is the formula to calculate the magnetic force. If there is a charge particle, if there is charge particle moving with some velocity within the magnetic field, then that particle has the magnetic force. To magnitude, I will be able to calculate by using this formula. So now force measured by newtons, charge measured by coulombs, velocity meters per second, and magnetic field units will be Tesla. According to that, Tesla is basically Newton over amperes and meters. Okay, so that will be the unit Tesla. Sometimes Tesla is a big unit, because of that we use the Gauss for the units if it is a small number of Tesla. Gauss is 10 to the negative 4 Tesla. Okay, now we discuss about how to calculate the magnitude. Now you can plug the values and calculate the magnetic force if you know the other things. But force is a vector. Now where the direction coming from? That's very important. Direction we need to find out by using your right hand rule. So now this is very important that you work on your side, because when I show my right hand, this is my right hand, but you're going to see it as left, right? Because the screen always get the mirror of our appearance, right? So that means this is my right hand, not the left hand. So you need to use your way by using the right hand. Okay, so now to calculate the direction of this force, we're going to use the right hand rule, or we call it as screwdriver rule, right? So the formula for that we already know. Formula is this one. And understanding of this formula, F will be greater if you have increase in charge. If it will be greater if your velocity is greater. If B is greater, it is greater. If theta equal 90 degrees, that's the maximum of the force. That's the idea about that equation, magnitude wise, right? But direction. So direction, this is what we're going to use. We're going to use your right hand rule, right? When you use in your right hand, there are 3 directions you can represent, 3 dimensions. Right? So one direction will be your thumb direction. Then you have 90 degrees between your thumb and your other 4 fingers, right? That means this one is one direction, this one is another direction. In addition to that, your palm is pointing to another direction. See it in here, this way. So this is third direction. There are 3 directions that you can represent by using your right hand: thumb, fingers, and your palm. Okay, so these are the 3 directions. Now always when you use the right hand rule for this one, this phenomena, you need to use your first, that means your thumb direction. This is my first vector, second vector, and the third vector. Third vector will be where my palm going to be open, right? First vector, second vector, third vector. So now in your equation, first vector, don't switch them. When you calculate the magnitude, it doesn't matter. But when you calculate the direction, it matters. Because of that, we are not going to switch it. We're going to stick into thumb into your velocity vector. And then those all four fingers, we're going to keep it into vector B vector. That means magnetic field vector. And then third vector, that your palm going to open up towards you in this case, that will be the direction of the magnetic force. Okay, again, this is my right hand, not the left hand, although you see the left hand. Okay, so now why this is important? Because it will change everything what will happen when the particle moving on the magnetic field. It will not stay in the same line. It will keep moving or make a circular path because of this force. That direction is important, right? Now let's take a example in here. We'll say, and first thing I want to mention that, let me see that if I, yeah. So now, you know that into the board and out to the board, I'm not able to draw, right? Because of that, there are two symbols usually we use. One is this symbol. That means some people use only the cross, but the usual symbol will be circle with the cross. So that will show you inward notation. Inward. If something is perpendicular, that means according to when you watch my screen, so you're going to watch in this side, that inward direction, right? That will be into the board, and outward means pointing towards you. So that is outward. That's a symbol for outward, right? Okay, so now we are ready to think about this right hand for the first example. First example means velocity, magnetic field, and magnetic force. That's the one that we're going to discuss. So now I have magnetic field in this way. Let's start somewhere here. Magnetic field that way. And there is a charge particle. I don't know what it is, but we'll say there is a charge particle Q, right? We'll say it is a positive value, right? It is a proton, okay? Positive charge or positive ion, okay? So now this particle is moving in velocity this direction. So now you need to identify what is your first vector is velocity, right? That means you need to point your this thumb to the direction of the velocity. When I point this upward direction, you need to make sure that your fingers are into the board, right? So you're going to point your thumb in this way, upward direction, that's the velocity direction. Now, since I'm in little turn, now my inward direction will be actually towards you in the screen, right? So that will be the direction of magnetic field, because magnetic fields is inward, thumb. And now what happened to your palm? You see that your palm is opening. If I take probably red pen because my image is small. Now your palm is going to open into my left side. Okay, so now you see right side, not the right side, because I'm working with this side. This is my left. Okay, so I'm seeing this vector to the left direction. So now because of that, my force direction is to the left for the positive charge I did. Okay, so now that will be the direction of the force. Okay, because of that, what will happen? Now I have velocity vector this way, force vector this way, then it will make a kind of resultant vector that way, and then it will keep rotating around the circle. That means that will do the circular motion because of that, right? So now I think it's easy to understand, but practice it a couple of times yourself. Okay. So now let's do this 3 example. In first case, I have a positive. I did not mention about the negative in here. Let's do it for the negative also. If it is a negative particle, what you're going to do, you just follow it as positive. At the end, after you do all the things and after you find the force direction, just do it in opposite direction. That means if it is a negative particle in here, sorry, go back. Sorry. So if it is a negative particle, what will happen in here is, we'll say this is a negative charge, right? So now finally we realize that positive particle, we have a leftward direction. But if it is a negative particle, you just going to switch the direction at the end. That means this particle going to move on this direction, right? Because of the negative. That's the only difference. Other than that, you are still going to use right hand, but just switch the direction at the end of the pause. Okay. And now let's do those examples. In first case, I have X, Y, and Z axis. Everybody know that if I have X, Y, and Z axis will be this direction, right? Perpendicular direction, similar to the third direction that we have. So I label that this is my X axis, this is my Y axis. Out of the board is my Z axis. Okay. So now I have a proton moving velocity, that is first vector, that is where my thumb is pointing. Thumb is to the left in this case, right? And then you have magnetic field downward direction, that means my fingers should go downward direction. Now my palm of the right hand is open towards me, that means outward from your screen, right? So outward from the screen, that means if it is a positive particle, I have the pose. I'm going to draw it here. Pose is outward direction. That means it is actually C direction. C direction is the pose direction. Positive C axis. Okay, positive C axis. Okay, so now let's go to the second one. Now forget about it is negative. We're going to switch the direction later. Think about it is a proton. Now you have velocity downward direction and C direction, a negative C direction is the direction of the B, right? So now you have hand, you need to rotate the hand accordingly. You have a hand like this. Your velocity is downward and B is into the screen. So now my palm will be open into positive x-axis. This is my positive x-axis, right? So now since it is negative, I need to do negative x-axis. So now this is pose will be towards negative x-axis. I'm going to draw it in here. Negative x. Okay. So now let's go into the last one. C. It's very important. You remember that your equation that F equal QVB sine of theta. Here sine of theta will be 180 degrees. 180 degrees sine theta means it will be 0, right? Because of that, there is no pose in this case. Pose equal 0. Okay, so I hope you guys get it. Okay. And you can do this example yourself. Try to do it a couple of times. I'm not going to do all of them, but let's try at least a couple of them. The first one will take a look. So it repeat the exercise negative charges. We're going to do it for the positive charge. So positive charge is going downward direction. That means my thumb should be pointing downward, but my my magnetic field is now outward direction. It is very hard to show. It is not this way. You need to do it this way, right? So that means you need to keep your fingers towards outward direction, right? So when you keep the fingers into the outward direction, don't know how to show you because it is very hard rotation in there. So now you have the fingers outward from there, and this is your thumb. That's the thumb should be actually downward. That's my mistake. Sorry for that. So we're going to do the thumb downward, but my finger should be outward direction. So I'm going to probably rotate like this, right? So it's I can do it in my side, but it is hard to show it in your side. You have V downward, B outward, then my palm will be open to the leftward direction, left. This is the direction of magnetic force if it is a positive particle. If it is a negative particle, direction will be right side. Okay, so now again second one, your thumb will be direction of velocity. Now my finger should be pointing towards the B direction. B is to the right and thumb is up. Then my palm will be into the board, right? So now in this case, I have into the board pose. Okay, So now next one, I have thumb point in that direction, but I should have my magnetic field inward, right? That means I need to keep my hand this way. This is my magnetic field. This is my velocity. Then your force will be upward direction, right? This case, force will be upward direction. It's very important that you try it yourself. Rest of the section, if you don't understand, try to go with your one of the friend and try to get it correct. Okay, so in this case there is no pause because they are anti-parallel to each other. And next case, actually velocity is inward and B is outward. So that means B is upward, but my velocity is inward. That means this is the way that I need to keep my hand. No, outward, sorry, inward. So that means this is the way that I need to keep my hand, right? Inward, upward, then there is a force acting on this direction. And then next one, I have velocity outward, but my force is, my magnetic field is this direction. Then you will see here, right? So outward, this direction, and then force is downward direction. If I do the mistake, you can talk in the recitation session. So that's, you need to do it, and also check with if you can do it in change in variables. Now in my right hand side, actually a magnetic field and force is given. You need to think what is your pulse vector direction is, right? So your magnetic field is this way, right? Magnetic field is outward, and then your force is upward. That means you need to keep your pin position like this. That means velocity will be to the right direction in here. Okay, let's try it again. Velocity, right direction, and this way, no, outward, and force is upward, yes. And next one, you have force upward, be that way, then you know that your force, your below B is this way, your force is upward. That means you should have thumb is pointing outward from the screen. Okay, this is the velocity direction. And next one, you have inward force and inward magnetic field, and force is to the right. So inward, force to the right. That means my thumb will be pointing outward direction, velocity. Okay, so repeat those process yourself until you get it. So if something is negative, this all the direction will be switch on to the exactly opposite direction. Okay, so now we discussed about the magnetic field lines earlier. So magnetic field lines always circular path, make as a circular, and B usually use the B symbol and measured by using the Tesla, right? So now if I have north and south pole, we know that how to draw the magnetic field lines. But if you have horseshoe magnet, that means north and south is staying like this shape, and then your magnetic field lines will be this way, right? If you have C magnet, then you have magnetic field lines in between this way. So these are some examples that we can see different situations. As example, you can levitate the objects by using magnet. As you know that if I have a north magnet in here, south magnet in here, then your magnetic field lines basically create in upward direction, right? Although they are circular in the other direction, if your world or the object is not heavier than your magnetic field strength, then you can levitate it. Okay? So levitation can be done by using north and south magnet if they are strong enough, right? And in addition to that, you can levitate the magnet this way or this way by using superconductors, because superconductors has the Meissner effect that will create the magnetic field lines that we can levitate the object. But only problem is superconductors are existing at very low temperature. Okay, so now everybody know how to do this one. If I have a couple of magnets, then if you draw the magnetic field lines always like north to south direction, then these points we call it as neutral point that does not have magnetic field lines. And this point neutral, this point neutral, points that do not have the magnetic field lines. Okay. Go back to our circulating charge particle. We know that if there is a charge particle moving with some velocity inside the magnetic field, that particle will do the circular path as we discussed because of the magnetic force, right? So now this is the example that you guys can see it in mass spectrometer and cyclotron and also cyclotron and also particle accelerator. That's how we accelerate the charge particles, right? But here I'm going to actually discuss your physics 1 class related to that. You remember that if there is a particle moving on the circular path in uniform circular motion, we discuss about the centripetal force. In this case, actually the force that we define as centripetal force is the magnetic force, right? So centripetal force, we know how to write it in physics 1, that is mass velocity square over radius of the circle, right? V is the tangential velocity. So now this centripetal force in this case will be actually your magnetic force. The magnetic force, we know how to write it, QVB, again sine of theta, since they are perpendicular to each other, the sine of theta will be just 1. So that will be equal to QV and B, right? So now you can decide according to the mass of the particle and according to the charge of the particle, your velocity and also velocity of the particle will define actually the path that particle will travel, basically the radius that will travel, right? So that's how the charge particle will move inside the magnetic field. So now, since we are talking about the perpendicular to the magnetic field motion, your particle will be always a circle as this, right? But it is not the real situation. In real situation, you can have the particle move in some arbitrary angle, not exactly 90 degrees. In that case, you need to take the sine of theta to the account in your equation, and then you're going to see this kind of helical shape structure of the motion of the charge particle. And also, in addition to that, your magnetic field is not always uniform. Uniform means it keeps constant, but it can change when the particle move from one place to another place. In that case, since the magnetic field is changing, then your shape of the motion of the particle, your circular loop, is not even a spiral shape. It will be make a spiral, but you have a bottle shape. There's some part you have longer radius because of the different magnetic field strength. Okay. So now next step, we're going to basically move into actually to get an understanding of electric and magnetic force together, right? This is called it as Lorentz force, right? So Lorentz force is combination of electric and magnetic force. That's the net force that object will feel, but definitely direction we need to take into the account by using vector addition, right? Let's take an example. So I have a positive terminal here, negative terminal here. We definitely know the electric field direction, right? So now if I have a positive charge particle in between these two plates, what we know is that positive charge particle has the electric force will be same direction as electric field. That's the force direction, right? Okay, so now I have particle moving from left to right in here, or positive terminal to negative terminal in here, but you see that there is a magnetic field by using this green color represent the magnetic field B, right? So now if you project the particle, this is the source, your projector, that you're going to project the particle vertically, right? So now what happened? If you have a particle vertically moving, use your right hand, vertical direction, magnetic field inward. Now what will happen? So you have force to the left direction. That's the magnetic forces, right? So now this particle has electric force, that is Q times E to the right. This has magnetic force, that is QVB sine of theta 1 in this case, QVB, that is to the left, right? So those are the two forces acting on this particle. That's called it as Lorentz force. And always velocity, and this is actually called it as the speed of light that later on we're going to discuss in your class. But ratio to electric field to magnetic field, only magnitude ratio, no direction. Magnitude ratio, E to B, we call it as the velocity. That is the speed of the light. Okay. And so cross field is next section, that since we know what is the electric and magnetic forces are, cross field is defined it. There are some examples for that. One is the Hall effect. But what is the cross field means? Cross field means if I have magnetic field and the magnetic force and the electric force are perpendicular to each other. If I have magnetic force and electric force, when they are perpendicular to each other, we call it as cross field. Okay, that's the definition of the cross field. So now Hall effect is an example of cross field. So idea is that if you have a magnetic field, you see that it is pointing outward in this direction. That's where you start your electrode. There is no labeling like positive, negative yet, but you have an electron with some metal piece within the magnetic field. So now if your electron is projecting towards this direction, we'll say we're going to project it by using some method in this direction, then this electron will feel the magnetic force downward direction. Okay, this is the magnetic force direction, right? So now because of that, actual electron will land on this terminal. Now if you project many number of electron, what happen is all electron will go to this terminal and all proton will stay on this terminal, positively charged. So now it creates the electrode that have positive and negative. Now because of that, electron will feel a force. Because of this, that will be electric force, right? So now electric force and the magnetic force will be in this Hall effect. That is called it as the Hall effect. Because of that, your particle will stay on the line when they are staying exactly in opposite direction. I think you get an idea. So if my F in this case, think about this. You create a positive plate in here and you create the negative force in here, then you have electron within the magnetic field outward that will create the magnetic force this way. If you can create the magnetic electric force in this way, if they are equal to each other, this electron can travel exactly in horizontal direction. But if magnetic force is greater, that will go downward direction. If electric field is greater, that will go upward direction, right? Whichever is possible. Okay. So now, cross field, again, next on that, if you have electric field and magnetic field are perpendicular to each other, as we discussed, that is what the cross field means, right? E and B are perpendicular. E and B are perpendicular, not the forces, field are perpendicular. So another example of that is discovery of cathode ray tube, Thomson experiment, right? So this is the physics behind the our television that found in earlier age, right? So if you need to project the electron from here to here, when you project it through your projector and when it go through the magnetic field, that actually should not bend upward or downward. It should go travel in the exactly horizontal line. To do that, there should be two forces acting on that. One is your electric force, other one is magnetic force, right? So now, if it is an electron, you know that how to use the direction. One will be downward direction. Definitely, if it is an electron, you know that this will go to the positive direction as your electric field, and it will have a magnetic electric force and magnetic force, they will be equal and opposite, then it will go through the horizontal line. If electric field is greater, then this is going to bend in this way, otherwise it will going to bend in this way, right? In addition to that, we're going to discuss about how this will change a little bit later, but this is what the idea about the cathode ray tube. And another example is the mass spectrometer, that the formula that we discussed, the bending of direction of electron or proton because of the magnetic field, right? So mass spectrometer actually separate ions to mass to charge ratio. That means positive ion may be bending in that direction, negative ion bending in that direction. So according to mass, your circular radius will be also different, right? So that's what it's saying in here. So you have positive charge, and then I have velocity of the positive charge this way, and then when it come to velocity on here, so now I have this proton. Actually, I'm working with proton in magnetic field inward. Now you need to use the right hand rule. You have magnetic field inward, and your thumb is the velocity direction. And then what happens? So then you have this direction of the force. That's why when I have force in this direction, velocity in this direction, it will take a circular loop if it is a proton. If it is a electron, it will do exactly same into the other direction. If it is a neutral atom, your particle is just staying on the vertical line in here. They are not bending. That's the main idea that we discussed so far, right? This projection of the particle, this velocity actually coming from because of this electric field. Electric field will create a velocity of the object, right? That coming from voltage. Okay. So now let's move into the, this is another example that you can think. I have 1, 2, and 3 path. You need to decide which one is neutron, which one is electron, which one is proton. So definitely the particle that will travel this way is a neutron, right? Now you need to think which one do the path of the proton, which one do the path of the electron. So now you have a velocity. If you start from here, this is the direction of the velocity of my first path, and direction of B will be outward. So B and to the left, so you need to keep your hand like this, right? B outward and B to the right, and then your palm will be pointing downward direction. That means since it is going upward direction, this will be your negative particle, right? So do the same in here. So you have velocity this direction and magnetic field outward. Now you're going to use your hand, thumb is upward, and my fingers are out to the board. Then you have magnetic force created in this direction. Because of that, this will choose the path this way. That's the proton is. In this case, I have okay, so according to that, you can define which particle that you are working with. Okay, so I think we are ready to move into the next part. That another definition that come with the magnetic field, magnetic force, right? So there can be a magnetic force if there is a particle, if there is a current carrying wire. Sorry, this is the second part, second system, that you have a current carrying wire inside the magnetic field. There is a current carrying on the wire, there is a magnetic field, but no charge particle. Charge particles are actually current with the velocity. We know that. Exactly same one, but in this case, velocity and time and charge, this everything we combine into the current and the length of the wire. So if I have current carrying wire inside the magnetic field, this wire has the magnetic force. Because of that, this wire will able to bend this way or this way, depend on your direction of the magnetic force, right? So that is next concept. So exactly same way we can calculate the magnetic force IL times B. That means it will be ILB times sine of theta, right? So now if there is no current, no force, right? No current, no force, but increase in current will increase F, increase in length will increase in field will increase. If angle is 0, that will be again 0. If angle is 90 degrees, then F will be max. Same right hand rule. Only difference is now instead velocity, I have to use the current or the length. Current and length are in the same direction. You can use the current direction. Then you will be able to find the direction of the magnetic force by using your palm opening direction. Okay, so now this concept is important, the thinking about the motors and like that, because motors are basically rotating of current coils, right? So what is actually happening? This one actually we have in the laboratory, that if you want to ask from someone, they can show you. So there is a high voltage supplier in here. There is a magnet. We know that there is a magnetic field lines north to south, right? So now if I have north to south, and then if I insert the current carrying wire inside that, if I switch on the voltmeter, this current carrying wire, in this case, going like pushing downward. You can see this in real eyes, that if you have enough voltage and the current to supply, and if your magnet is strong enough, right? And now why it is happening? Because you're going to use your right hand, magnetic field from left to right, right? That is this direction, and your current direction is into the board in this case, right? Into the board, and this way. This is how you're going to keep it invert. Then your palm will be this way. That's why this wire is forcing downward direction. This wire is bending this way, basically, right? So now, in any case, if you switch the direction of the current, you're going to bring the current now outward direction. Now you have still magnetic field in that way, but my current is now outward direction. That means I need to keep in this way. Outward means you don't see my thumb, but thumb will be in this plane, right? Then you have the magnetic force upward direction. Because of that, this wire will jump out from your setup. Okay. Okay, so now some more examples. By keeping the wire inside the magnetic field, usually they will rotate. What will happen is, you see that you have the current in here, magnetic field outward. Use your right hand rule, right magnetic field outward this way, and then you have force on this wire in this direction, right? If you do exactly same, you will see the force on this wire in this direction. They will be usually cancelled out if they are the same size. But in the bottom, what will happen is you have current. You see that the current is counterclockwise in this case. So that has the direction of there, but your magnetic field is outward. Then you have magnetic force acting on this direction, right? Because of that, if you have magnetic force greater than the weight of this coil, this will go downward direction, right? In addition to that, current coils that we have, always current loops, right? Current loops, always the motors that will, electric motor, how this will work, right? You have, basically you have magnetic field lines, these green lines are B, and then in this case, you have current into the board, and this case, you have current out to the board, right? So you're going to apply your rule that current is invert and magnetic field is that way. And then you have force downward direction for this one. If you do upward, will be this one. Now, if you have downward and upward force, this will rotate the clockwise direction, right? So now this will not keep rotating. What will happen is these two coils stay in like this. Then they're going to rotate into this direction. When they rotate into this direction, then it will be parallel to your magnetic field lines. Then there is no force acting on any of the turns of the coil. Then you need external force from outside by using magnets or by using AC current, you can switch the direction. Whichever way that we are doing externally will helpful for you to rotate this back and forth. That's how the electric motors will work. Okay, so I'm not going to take much time on here. Electric motors, when you have the rotation, we definitely know there is a torque created by rotation. That torque will be able to calculate by using the force, because we know that the tau we can calculate by using R times F times sine of theta in physics 1, right? If you have R in here, you see that this is my pivot axis that we're going to rotate, and this is the distance from here to here is W over 2, and then one of the force will create the torque that will be W over 2 times F times sine of theta, and the other side also do exactly same. That will be W over 2 times F times sine of theta. Then you're going to add these two together. That will be your net torque. That's why I have it in here. W times F times sine of theta. That's how you calculate the torque of the rotating coil, right? And in addition to that, my next slide is explaining how to input this force, because force we will be able to calculate by using current, length, if the current and length usually they are perpendicular, right? Current and length are usually perpendicular. Current and the B are mostly perpendicular. Because of that, I will be able to put that one into there, and then we can write the final equation as tau equal I, W, L, and B, and sine of theta. And W and L will be actually this cross-sectional area. You see, W here, L here, and if you take this cross-sectional area, that is the W and L means. Okay, so now final equation I will be able to write. That's what I have it in next slide. So this will be able to write I times cross-sectional area times B times sine of theta. Okay, so now in addition to that, usually you don't have a single coil. You have many loops. If you have many loops, you just need to multiply times number of loops. That will give you the torque of the your rotation of the current coils. Okay, so now again, this formula that I just derived is here, right? But what this means? This means is, you see that when the theta is 0, right? When the theta is 0, that means your direction, think about it here. So your direction that you had in between your W and the post, that's perpendicular direction in this case, right? If it is 90 degrees, you're going to have maximum torque. But if they are parallel in any case, that's what happened in my earlier example that I mentioned in here. When they are going to parallel, basically no torque, right? Then your torque will be 0. That's what the sine of theta means. Okay. I think I will stop in here. We will talk about more about this chapter in next section.